Welcome to Brother Joseph Musonda's YouTube channel. This is a YouTube channel where I don't teach mathematics using the traditional methods or the methods that are already known. It's a channel where I teach my own methods or formulas that I create by myself. That is all what this channel is focused on. It's teaching innovative ways of solving mathematical problems using Musonda's mathematical methods. In today's video, I'll be showing you how we can solve the linear systems of equations using Musonda's method in 3 variables. Last time in the video I posted, I was solving the systems of equations using Musonda's method in 2 variables. Now remember the comparison of this method with Cramer's rule. Musonda's method uses 2 determinants to solve problems of 2 variables and uses 3 determinants to solve problems of 3 variables. So let's quickly look at the problem that we have. That is the problem that we have, linear systems of equations in 3 variables, which needs to be solved, of course. So we shall quickly go to look at 3 determinants, one determinant for x, the other one for y, the other one for z. So let's move on and look at the arrangement of the elements, which is 3 by 3 matrix there for x. Then we look at the determinant. So the way this determinant is found, or the determinants are going to be found, it's the same way that we find the 3 by 3 determinants. So the determinant in this case representing x, we have is 64. So we move on to look at the determinant representing y, and that determinant representing y is simply 32. If you pause the video, you can solve for the determinants of x, you can solve for the determinant of y. You'll be able to find 64 for x, also 32, that is for y. So now we are remaining with the determinant for z. So let's see how the determinant of z comes out also. So we have the elements here expressed in matrix form 3 by 3 for z. Then finally we have a determinant which is 80 for z. Now that we have the 3 determinants, we can move on and find the denominator that we'll be using to calculate the actual values. This denominator is not a determinant. It is simply what looks like this. I am calling this denominator, should I say, as m. And how do we find this denominator? We can either use the first equation, or we can use the second equation, or we can use the third equation. We are going to correct the coefficients of those equations. Whichever equation that you use, you correct the coefficients, and you multiply those coefficients with the corresponding determinants. So in this case, I picked on the first equation, and the coefficient of x in the first equation, if I may take you back to look at the coefficient, it's actually 3. This is my first equation, the coefficient is 3. Then the second one, which is the coefficient of y, is 2, and the coefficient of z in the first equation is -1. While the constant here, which is our d, is simply 11. So I have my A1, which is a 3, A2, which is 2, then should I say B1, A1, I have 3, B1, I have a 2, C1, I have a negative 1, and my D1 is positive 11. So we get back and see how the denominator is in fact found. So we are there looking at how the denominator is found. We multiply those coefficients from the first equation by the corresponding determinants. So there we go. You can see 3, which is the coefficient in the first equation, multiplied by the determinant of x, then positive 2, which is the coefficient of y in the first equation, multiplied with the determinant for y. Then I have negative 1 as the coefficient from the first equation, which is the coefficient of z, multiplied with the coefficient, should I say the determinant of z. The overall result is simply 176. So we use that as the determinant. Check how the formula comes out. So to find x, we need to multiply the constant, because I'm using the first equation. We multiply the constant from the first equation by the determinant of x. Remember, when you are finding x, you multiply the constant from that particular equation you are using to multiply the constant times the corresponding determinant of what you are finding. In this case, it is the determinant of x. So you remember from the first equation, our d1, which is the coefficient, should I say the constant from the first equation is 11. We are multiplying it with the determinant of x. Then we divide by the denominator, which is 176. So when we multiply 11 by 64, we have 704 divided by 176. That gives us a 4. So the formula for finding the value of x is simply the constant of the equation that you are using multiplied by the corresponding determinant of what you are finding, in this case, which is x, then divided by the denominator. This denominator is going to be used throughout. So it's a common factor. In other words, I shouldn't say the common factor. It's something that is constant. We need to use it in all the 3 steps or the 3 sub-formulas that we are using to find the solutions. Let's move on and look at how we can find the value of y. So the value of y is equal to the constant of the first equation multiplied by the determinant of y over the denominator. So that is 11 times 32. 32 is the corresponding determinant for y. Then we divide by 176, which is equal to 352 over 176, and the result is 2. We move on to the last one, which is finding the value of z. It is equal to the constant of the first equation multiplied by the corresponding determinant of z divided by the denominator. So remember, what is the determinant of z? It is in fact here 80. So we are multiplying with the constant from the first equation, and the result is 880. Then we divide by 176. The solution is 5. So that marks the end of this video, and I have simply shown you how the Musonda's method can be used to solve linear systems of equations in 3 variables. I also want to tell you that stay groomed to stay connected to my YouTube channel, because on Christmas Eve there is something that I'll be dropping as a Christmas bonus or gift to the global mathematics community. It involves the formula for finding the prime numbers and the proof for Goldberg conjecture. Thank you for watching, and If you can share this video to other platforms, I'll be very glad indeed. Thank you very much.